There is very little variance in that. So you can't adapt in that way. Why is it that Hemsbok can survive in the Kalahari and Angus, prize Angus bulls from Scotland can't? Is because the prize Angus bulls from Scotland are too stupid. Okay, they stand in the sun. Okay, you won't find a Hemsbok doing that. So most of the adaptations are behavioral rather than physiological. And the same, I would venture, applies to humans as well. And when we had these heat waves in South Africa of just a year ago, we actually did start picking up increases in mortality, particularly in, for instance, informal settlements, people living in tin shacks, okay, no cooling, no ventilation, the elderly, okay, people who were water stressed, okay, so we are not immune from this either. And there have been similar studies, for instance, in Pakistan, had a big heat wave last year. Again, here's a place that's used to heat, thousands died. Okay, so don't just think that we're tough boykies, we can handle the heat. Okay, we're also susceptible to this. We have the same basic physiology. And it's about how we adapt ourselves, adapt our urban design, adapt our behavior that causes us to succeed or not to succeed. So that 2015-2016 El Nino was one of the strongest El Ninos on record. And I want to make a little side point here, because it is relevant to the question of denialism. And that is, there was a very famous argument that the world temperature between 1996 odd and 2013 odd, okay, hadn't gone up. Okay, there was a lot of variation, but you looked at it, there was the so-called hiatus, where the world temperature hadn't gone up. But the CO2 had gone up. See, CO2 went up, temperature didn't go up. There is no connection between CO2 and temperature. Okay, well, wrong. Okay, and the main reason for that is that most of the temperature which is captured, most of the additional energy which is captured, doesn't go into the atmosphere. If you look at the heat contents of the different parts of the climate system, the atmosphere is only about 1% of the heat content of the Earth climate engine. Almost all of it is in the oceans, okay, and then a large chunk of it is in the ice bodies. So the energy over that period was still being captured, okay, but it was being allocated, it was being transmitted into the oceans over that period. And if you look at the ocean heat content over that period, 96 to 26, it just kept on going up. There was just this, disconnect from the atmosphere because it was going into deep ocean heating. That has to end at some stage. The oceans reorganize, whoa, there's now all this hot water, it's got to, reorganize the circulation, and that manifests itself as like the biggest El Nino on record, this massive pool of warm water which developed in the Pacific. And so the world atmospheric temperature is no longer in hiatus, okay? It's rising again, and it has gone through those hiatuses repeatedly over the instrumental record. There was a long hiatus in the 1960s, there was one before that. So that's just a feature of the world climate system. As you push energy into it, it goes into these various long-term stores, then eventually the atmosphere catches up, okay, and it does a correction like that, okay? So that was the sort of underlying reason for that. So as a result, high temperature records were broken all around the world, including in South Africa. There's just been an announcement the last 3 years have been the warmest years on record. And that is a combination both of this El Nino effect, okay, during that period, but also the fact that we have this rising baseline, that the mean has been rising steadily over time. And when you unpack that for Southern Africa, it's about half-half. About half of the extreme heat that we measured in that 15-16 period was due solely to the shorter-term dynamic, the sort of decadal dynamic of the El Nino, and about half of it was due to this anthropogenic, century-long dynamic that was underlying it. So the point is that we have very good proxy records, that the El Nino phenomenon is nothing new to Africa or Southern Africa. So you can go and look into a whole lot of different proxies. You can look into stalactites, you can look into tree rings, and we can detect El Ninos going back at least 1,000 years. You can also pick it up in newspaper records and travelers' records and things. So we can detect that there have been El Niños for a long time. So climate change didn't create El Niños. Okay, El Niños have always been there. But something has happened to their statistical structure. So up until 96, we thought we had this one completely nailed. Okay, so we had a way of projecting the rainfall in the next year to 18 months based on sea surface temperature records from the Pacific and pressure differentials between Darwin and Fiji. Okay, you created something called the El Niño Index, and it was a leading index of wet or dry in South Africa, where the lead was about 12 to 18 months. And so we had with great confidence, we would say there's an El Niño coming up. Farmers don't plant this variety of maize, rather plant that variety of maize, or plant late, or plant sorghum instead of maize, and it would usually work out pretty well. And we got really confident in that, and so there was a giant El Niño, developing in the period of about 1996. And we came out with a very confident prediction: there's going to be a drought. Don't do it. Well, there wasn't. Okay, and as a result, a lot of people lost a lot of money, and a lot of people probably went hungry as well because they, planted the wrong crops. So here's a real problem. You have to be really careful about making these projections. If you don't have, you can cause as much damage by giving a wrong projection than by not giving a projection at all. So we had to go back to the drawing board to try and understand why is it that our statistical understanding of El Niños, no longer applied in the future. So it seems, and this is not just a Southern African phenomenon, that something about the internal dynamics of El Niños is changing. Okay, we don't really understand where that's going. We don't know whether it will continue into the future. It is consistent with the modeling of future climate change. You can't ramp up the energy cycle of the world and not change the ocean circulation. That has to follow, but that's a 3D turbulence problem, really, really difficult to predict, with any confidence going into the future because of all the problems of complex systems. So we anticipate that the El Niño will change. We have observed it's changing. That's consistent, that's not proof, and it's not predictive. We can't say, in future, this is going to happen. But the good news is we have, in fact, recovered some of our predictive ability because we've changed the way that we're making El Niño projections. Instead of making it a purely phenomenological, statistical prediction, here you've got a signal, it correlates with something that happens here, therefore we can make a prediction on it. We now actually have a quasi-mechanistic approach to doing that, where we actually collect. So the reason that there is persistence in El Niño, which is the reason that we have a predictive capacity, is because it's based on this big body of warm water. And once you've observed this big body of warm water, it doesn't disappear overnight. It's got to move, in certain directions and at certain rates. And so once you've got that understanding, you can actually make a relatively good prediction of what's likely to happen. And that's the basis on which we now make our El Niño predictions for Southern Africa. It's not this correlative approach. It's we take the observed three-dimensional energy contents of the ocean, we put them into a model, and we run the model forward. So it's quasi-mechanistic. It's the model that's doing it rather than just statistical. Okay. So the question then really is, how can we be sure that El Niño has changed? We have a strong feeling that it has because our statistical models have failed. In order to prove that it's changed, you would have to have a whole sequence of records. Now, I remember being told by a very wise person many years ago, 2 humps doth not a cycle make. Statistically, you actually need about 5 humps before you can actually say what is the periodicity of a cyclic phenomenon. So if we say that El Niños occur, severe ones in this area, about once every 20 years or so, we would need a 100-year record before we could detect whether there'd been a change. We think that this change in the El Niño has occurred in the last maybe 2 decades. We don't have nearly long enough record to be able to say, no guys, El Niño now follows this dynamic rather than that dynamic. And it's not sure that it'll work like that anyway, because we might simply be in a transient and we have no idea where the endpoint of that will be. Right, so my final point is that especially especially as members of the public or members of the media, you're getting all this conflicting information. This guy says that, this guy says that. How do I sort out from this lot what matters? And this audience is particularly important because you, in fact, are, for many of the public, the go-to audience, the interlocutors, the brokers in that process. So being clear about how we sort out conflicting evidence and certainly into what we know, what we don't know, and what our responsibilities as scientists are to say about what we know and what we don't know, and what our uncertainty is and how do we communicate that, is a really critical issue. So the first point is that as scientists, and I include everyone in the sort of science domain amongst scientists, engineers, medics, whatever, we are trained to be skeptical. It's one of the things I teach my students. Don't just accept the data. Don't accept because I said so, okay? You've got to think this one through. Does it make sense, okay? Does the data stand up? You must be skeptical. And all of you, I'm sure, have had the experience of going to a dinner party and talking about some arbitrary subject and putting on your skeptical scientist hat, and everyone looks like you've brought a bad smell into the room. That's just the way we are, and usually we have to learn to control it, because it can be quite damaging in discussions which really don't require that degree of analytical rigor. But we're all, trained as skeptics. So I expect climate scientists to be skeptical. And there is a strong debate within climate science about many of the details of global change. A particular one is our ability to correctly represent and predict clouds. So clouds have a huge impact on the climate, mostly not because they bring us rain, but because of the fact that they change the albedo of the world and the transmissivity of the world, and it makes an enormous difference whether the cloud is down here or the cloud is up there, whether the cloud's made out of water or whether it's made out of ice, and getting those details right in a global climate model is phenomenally difficult. Imagine trying to simulate that microphysics in a grid cell of 50 kilometers. Okay, it's actually just a very difficult thing to do. Now we're making a lot of progress on that, and there's lots of debates about the best way forward. But that's an example of the raging skeptical debate within the climate community. No, you can't possibly do it that way. You've got to do it this way. This way is better than that way. That doesn't mean that the scientific community, climatologist, thinks that climate change is a bunch of hokum. Okay, it's that we are discussing the details, okay, the representation and the mechanism. You can make an analogy to evolutionary science. Every now and then, if you've ever hung around with evolutionary scientists, you know that they fight like cat and dog around the details. Doesn't mean that they're rejecting evolution. They all believe in evolution. They're arguing about whether it's continuous or punctuated, or whether epigenetics matters or doesn't matter. This is the detail. It's not the fundamentals. Okay, so. But the point is that when you're looking at these things scientifically, you are obligated to follow the rules of evidence. You have to obey your training about what constitutes good evidence, what constitutes solid data sets, what constitutes scientific fraud, okay? And you have to acknowledge your uncertainties. And that runs us into a lot of trouble communicating with the public and with policymakers, because every time the scientist says something, they kind of feel that they have to say, put in the ifs and the buts. Okay, that's our training, to say this is what our uncertainty limits are. And if you're not trained in that method, and you listen to two people speaking, and the one says, well, here are all the caveats, and the other one says, it's like this. And you say, I'm going to go with the guy who says it's like this. He obviously knows what he's talking about. Okay, and so that's something that we all struggle with. How much of that hedging around with detail do we do? And within IPCC, there's a particular language which is developed for that, to be as unobtrusive as possible but maintain the traceability, and that is done very rigorously. Okay, you don't just slap in the words like high certainty. You can't just yourself decide what's high certainty. It has to pass a whole set of tests and things like that. And you only use that language at the highest level of communication. In your general writing, you don't put every sentence hedged about with these ifs and buts, because it just makes it completely unreadable. But we do have an obligation to acknowledge uncertainty where it is critical to the decision-making process. So how do you then separate someone who's skeptical, and rightly skeptical, from someone who's simply a denialist? Well, the acid test I use is what happens when you confront them with evidence. When you confront denialists with evidence, they either just ignore it or change the subject, okay, and then just go back to what they were saying before. It's completely impervious to evidence, and we all know debates like that. There are typically debates about, for instance, theology, okay? They have nothing to do with the evidence. They have to do with your belief system or whatever. So the difference between, for me, a skeptic and a denialist is the willingness to engage with evidence, okay? And so if you have a source, and you need to now, as a person who's trying to interpret this, how do you go about evaluating whether this is a legitimate source or not? Well, there's a couple of things that you can do. First of all, look at the qualifications and track record. You know, does this person have any basis for making the claims that they're making? And you have to be really careful here, because many of the denialists, okay, are professors, or have won Nobel Prizes, or done something grand like that. But if you look at the area in which they have their professorship, or the area in which they've spent their life research on, okay, it may have absolutely nothing to do with the thing at hand. And just because I'm a professor of systems ecology doesn't mean I have any insights whatsoever into a subject which is far from my domain, okay? I'm just an ordinary O, okay, with respect to that subject. I can't pronounce, you know, very helpfully about the HIV epidemic, or the ethics of, you know, this or that or the other. I'm just an ordinary citizen, you know, in that respect. So the fact that you're bringing, you know, the credentials to the table, you need to test those credentials. Are they in fact applicable to this area? So that's the first test that you do. The second is, are they actually putting evidence on the table, or is this just assertions? And is it in fact traceable, verifiable evidence? An example, no names, no pactoral. There was one very prominent denialist in South Africa who argued that he had a long-term climate record which showed that there was no climate change at all. This was simply a solar variation phenomenon. But nobody else could have the data set. Okay, and if you got independently the data set was based and you applied, you know, your analytics to it and it showed nothing, that's because we weren't using his proprietary method of analyzing it. Could we see your proprietary method of analyzing? No, it's a secret. Okay, all right, so, you know, you've got a little problem there. If stuff has to be, you know, verifiable, it has to be in the public domain, you know, the data sets have to be associated in the supplementary material of the paper. This is detail, okay, and it's not the sort of detail that you would expect ordinary members of the public or even, you know, journalists to pick up on, but that's how you tell what is, you know, genuine from what is flim-flam. Then are these findings published in peer-reviewed journals? Okay, people say, oh, but it's all been published. We go and try and find out, you track those publications, and they all end up being in the Sunday Times, okay, or the Bopsfontein, you know, Horticultural Society minutes, all right, and including some very, very prominent people. For instance, the very famous skeptical book by Lomberg. Someone very diligently went through and traced all these references. It looks like a scientific paper. It's full of references, you know, footnotes and whatnot. Someone went and diligently traced them, and almost all of them were either self-references, okay, or they were to untraceable sources, okay, or they were to websites, or they were to things which didn't go through any kind of peer review process. So that's another test that you apply, okay. And then, to me, one of the key things is, do they keep on bringing up long-buried controversies? And I've raised two in the last, you know, presentation. The one is this issue of whether, in fact, the world's temperature has gone up, or was this just fudging due to the way they statistically treated the data? Now, that has a corollary in something called the hockey stick controversy, which basically says that the world's climate, from our proxy records, had been pretty flat through the last 1,000 years, and then the last 150, it has shown this uptick, and that's called the hockey stick. And this was challenged in the United States Congress, very personally. People's careers were destroyed, you know, et cetera, went after very aggressive. Well, there have been 8 separate judicial studies of that. They've all found it to be well-founded. Okay, the hockey stick exists, no matter what statistical approach you apply, etc. All right, but you will see the same thing being brought up repeatedly in the denialist community, as if this had never been resolved, if it hadn't been looked at 8 times and found to be absolutely solid. The same thing is around the hiatus. The hiatus is well and truly over, okay? The world temperature is going up. The apparent discrepancy has been well described, okay? Boom, it comes back up again. The world didn't warm up. The CO2 went up, but the world didn't warm up. That's a resolved issue, okay? And it's because many of these people actually just go back to the same websites to pull off their case studies, and those don't ever get changed. So they just keep on repeating the same discredited stories. So there's my kind of pointers to how do you actually sort out what's noise from what's legitimate discussion in this field. And that's a good place to end. Well, we're not ending, of course. That's just the sort of opening positions. Any questions? And then I think we should have a discussion.